Welcome. Take a moment to settle in. Without trying to find the perfect position, turn the volume down to the point where my voice is only just audible, a little below what would be comfortable in daylight. Nothing that follows needs to be remembered, or understood, or followed to the end. You can fall asleep at any point, and you will not miss a thing. Tonight, we are going to talk about the universe, slowly, without hurrying. You have stood outside at night, somewhere far enough from streetlights that the dark actually held, and tipped your head back until your neck began to complain. The cold worked its way through your sleeves without hurry. After a few minutes, the sky filled in, faint stars appearing at the edges of your vision where a moment earlier there had been nothing at all, and the whole arrangement seemed to settle closer around you. Every point looked the same distance off, pinned to one dark ceiling, none of them nearer than another. Nothing about the act of looking up tells you which is which. Everything known about the sky arrived here as light. No one has traveled to a star. No sample has ever been scooped from one. And the entire body of knowledge about what burns out there, what it is made of, how hot it is, which way it is moving, and how far off it lies, was extracted from beams of light falling on the ground. The method is to catch as much of that light as possible with a curved mirror, spread it out by color so that it stops being a single point of brightness and becomes a long band, and then read the fine structure written across that band. Distance comes from the same source, worked out by comparing how bright a thing appears with how bright it must truly be, or by watching how its position shifts as the Earth swings around the Sunday. The sky was measured without anyone leaving the ground, because light does the traveling, and light carries a record of where it has been. Tonight, on a plateau in northern Chile, that process is running. The Atacama sits high and dry between the Pacific and the spine of the Andes, and the cold current offshore and the mountains inland conspire to strip the air of nearly all its water. Some weather stations there have gone years without recording measurable rain. Observatories are built on ridges above 2,000 meters because the air overhead is thin, steady, and almost free of vapor, and because there is no city close enough to spill light into the sky. The domes open at dusk, fans push the day's warmth out of the buildings, so the inside air matches the outside, and the metal begins to cool towards the temperature it will hold all night. Consider one particular beam. It left the surface of a star a few hundred years ago, spreading outward in all directions, thinning as it went, so that by the time it reaches the Earth, only a minute fraction of what was emitted arrives anywhere near this hemisphere. A dark-adapted human pupil, open to about 7 millimeters, intercepts a portion of that so small the star registers as a faint prick. A mirror 8 meters across intercepts something over 1,000,000 times more. And this is the first and simplest reason for building large telescopes. They are buckets, and the sky is a very light rain. The mirror itself is glass, ground into a shallow curve accurate to a fraction of the wavelength of the light it handles, and coated with a film of aluminium so thin it would take hundreds of layers to reach the thickness of a sheet of paper. Behind it sits an array of actuators, pushing gently on the underside, correcting the sag that the glass takes on as the telescope tips towards different parts of the sky. Light strikes this surface, folds back up to a smaller mirror near the top of the tube, and comes to a focus at a point where an instrument waits. In many modern telescopes, it does not stay there. An optical fiber picks the beam up and carries it down through the structure, out of the moving parts, into a sealed room where the temperature is held constant to a fraction of a degree and the air pressure is kept steady, because a spectrograph that flexes or breathes will lie about the thing it is measuring. Inside that room, the beam is straightened by a collimating mirror and then thrown against a piece of glass cut as a prism, or more often against a grating whose surface carries thousands of fine parallel grooves for every millimeter of its width. Either element does the same job by different physics. Blue light bends more than red, or interferes constructively at a different angle from red, and the single white point of the star opens out into a ribbon running from violet through to the deep red and beyond. A camera lens focuses this ribbon onto a detector, a silicon chip cooled with liquid nitrogen so that its own warmth does not fog the picture, and the exposure begins. What comes out is not a smooth rainbow. Crossing the band, at fixed positions, are narrow dark gaps where light is missing. Some are faint and easily overlooked, others are broad and heavy, cutting the spectrum almost to black. Their pattern is not random, and it does not shift with the mood of the instrument. The same star, observed from a different mountain with different glass, produces the same arrangement of gaps in the same places. They exist because of what happens in the outer layers of the star. Deeper down, dense gas radiates across the whole range of colors at once. On its way out, that radiation passes through cooler, thinner gas above, and the atoms in that upper gas will absorb only very particular amounts of energy. An electron bound to an atom cannot sit at any energy it likes. It occupies one of a set of fixed levels, and to move from one to another, it must take in exactly the difference between them, no more and no less. A photon carrying precisely that amount gets swallowed. A photon carrying slightly more or slightly less passes through untouched. Since the energy of a photon corresponds directly to its color, each kind of atom removes light at its own list of wavelengths and leaves the rest alone. Every element, therefore, has a signature, unique and unmistakable. Sodium takes a close pair out of the yellow. Hydrogen takes a series in the red, the blue-green, and the violet, spaced in a pattern that tightens as it climbs. Iron, with its complicated tangle of energy levels, takes thousands of narrow slices scattered across the whole range. And it is largely iron that gives a solar-type spectrum its densely ruled appearance. Laboratory measurements on Earth establish which lines belong to which substance and at what wavelength, so reading a stellar spectrum becomes a matter of comparison. Along with the star's light, the instrument records a lamp of known gas through the same optics, and those reference lines mark out the scale like the graduations on a ruler. From the depths and shapes of the lines comes more than a list of ingredients. A line's strength depends on temperature as much as on abundance, since an atom must be in the right state to absorb at all, and the balance of lines across a spectrum gives the surface temperature to within a small margin. Pressure in the star's atmosphere smears the lines wider, which distinguishes a swollen giant from a compact dwarf of the same warmth. Rotation smears them too, in a characteristic way, because one limb of the spinning surface is approaching while the other retreats. That last effect points at the other great quantity the spectrum yields. When a source of waves moves towards or away from the receiver, the measured wavelengths are compressed or stretched. The whole signature slides bodily, all its lines together, keeping their spacing and their relative depths, but sitting at wavelengths slightly shorter or slightly longer than the laboratory values. Because the pattern is recognizable even after it has moved, the size of the displacement can be turned directly into a speed along the line of sight. Instruments in these Chilean domes are stable enough to detect shifts corresponding to a walking pace, which is how the small back-and-forth tug of an unseen planet is registered in the light of the star it orbits. Mauna Kea rises out of the middle of the Pacific as a broad shield of old lava, and its summit stands a little over 4,200 meters above the water that surrounds it. Measured from its base on the sea floor, the mountain is far taller still, though for astronomy only the height above sea level counts, because what matters is how much air remains overhead. At the summit, roughly 2/5 of the atmosphere by mass already lies below, and the fraction that stays above is not only thinner, but drier and stiller than anything found at lower ground. Every observatory built on a high, isolated peak is buying those three qualities at once, and paying for them in cold, in wind, and in the difficulty of getting people and glass to the top. Water vapor is the first thing left behind. Over the tropical ocean, a layer of warm air settles above the cool marine surface at around 2,000 meters, and that boundary caps the moisture and the cloud beneath it. Above the cap, the air holds so little vapor that the total column, if condensed into liquid and measured as depth, often amounts to less than a millimeter. Since water molecules absorb strongly across much of the infrared, that dryness opens windows in the spectrum that are simply shut at sea level. Cold dust between the stars, the warm envelopes around forming suns, and the red-shifted light of distant galaxies all arrive at wavelengths the lower atmosphere would swallow. Steadiness is the second quality, and it is the harder one to obtain. Light from a star has crossed years of near vacuum and arrives at the top of the atmosphere as a set of essentially flat wavefronts, all parts of the beam in step. The final few thousandths of a second of the journey ruin that regularity. Air of slightly different temperature has slightly different density, and therefore bends light by a slightly different amount, and the atmosphere is full of such parcels, mixing and shearing at every scale from hundreds of meters down to centimeters. Differences of a few hundredths of a degree are enough. By the time the wavefront reaches the mirror, it is corrugated, with some patches arriving marginally early and others marginally late. At the focus, that corrugation does not produce a single point of light. The beam interferes with itself, breaking into a scatter of bright speckles that shift and reshuffle hundreds of times each second, and a photographic exposure of even a fraction of a second averages them into a soft, round patch. Astronomers call the width of that patch the seeing, and they measure it in arc seconds, an arc second being 1/3600th of a degree, about the angle a coin would subtend from a distance of 4 kilometers. Ordinary sights deliver 1 or 2 arc seconds. Mauna Kea on a good night delivers less than half of one. A 4-meter mirror, if the air were absent, would resolve details some 30 times finer than that. Because the distortion is imposed near the ground rather than at the telescope, a curious limit follows. The atmosphere stays coherent only over patches of 10 to 20 centimeters across for visible light at a decent sight, so a mirror wider than that patch collects several mismatched pieces of wavefront at once and combines them into blur. Enlarging the mirror gathers more photons, which is worth a great deal, but it buys almost no additional sharpness. That is the arithmetic that governed observatory design for 3 centuries. The great reflectors of the 19th and 20th centuries were light buckets first and image formers second, and the finest nights were the ones when the sky briefly held still. Naked eye twinkling is the same phenomenon at a coarser grain, with the whole star flickering in brightness as the wandering patches of air focus and defocus its light. Planets, showing a small disk rather than a point, average over many such patches and shine steadily, which is a reliable way of telling one from the other without any instrument at all. The characteristic time over which the pattern changes is a few thousandths of a second, and that number sets the pace at which any correction must operate. Choosing where to build is therefore partly a study of wind. Air that has traveled a long way over open ocean arrives smooth, layered, and free of the eddies that terrain generates. And a summit that stands alone in that flow disturbs it as little as any place on Earth. The remaining turbulence tends to be produced by the observatory itself. A mirror warmer than the night air sheds a plume of its own, and a closed dome full of yesterday's heat ruins the very seeing the mountain provides. Modern enclosures are ventilated so that outside air washes through them. The mirrors are cooled to match the sky before dusk, and heat-producing equipment is moved out of the light path or insulated. Adaptive optics attacks what the sight cannot supply. A portion of the incoming beam is split off and sent through a grid of small lenses, each forming its own image of the reference source, and the displacement of each little spot from its nominal position reveals the local tilt of the wavefront over that patch of the mirror. A computer stitches those tilts into a map of the whole distorted surface and calculates the opposite shape. That shape is applied to a thin, flexible mirror, pushed and pulled from behind by hundreds or thousands of actuators moving through distances measured in fractions of a micrometer, and the beam reflects off it corrected. The whole cycle repeats itself several hundred to a couple of thousand times a second, continuously, for as long as the observation lasts. The method needs something bright enough to measure, and it needs that something close in the sky to the target, since the correction is only valid over the narrow cone of air the reference light actually traveled through. In visible light, the usable radius is a few arcseconds. In the infrared, somewhat more, and suitably bright natural stars sit beside only a small percentage of interesting objects. The solution, now standard on large telescopes, is to make a star where one is wanted. Between 80 and 100 kilometers up, there is a thin layer of sodium atoms, replenished by the vaporizing of micrometeoroids, and a laser tuned to the yellow wavelength those atoms absorb will set them glowing. Projected from beside the telescope, the beam paints a small artificial point in that layer, and the wavefront sensor works from its light. One thing the laser cannot supply is the overall tilt of the wavefront, the slow wander that moves the image bodily across the field, because the outgoing beam is displaced by the same air on the way up as the returning light is on the way down, and the two effects cancel in the measurement. For that component, a real star is still needed, though it may be faint and comparatively far off, since the wander changes more slowly and over a wider angle than the finer distortions. Infrared work adds a difficulty that no mirror shape can remove. At those wavelengths, the sky glows, the dome glows, and the telescope glows, all of them simply because they are at ordinary temperatures, and the astronomical signal arrives on top of a background far brighter than itself. Instruments are therefore sealed in vacuum vessels and chilled with liquid nitrogen or liquid helium, Their optics and their detector arrays held tens or hundreds of degrees below the surrounding air, so that the apparatus contributes as little of its own radiation as possible. Observers alternate rapidly between target and blank sky, subtracting one from the other, so that whatever both frames share falls out of the arithmetic. People fare less well at the summit than machinery does. The air there holds around 60% of the oxygen available at sea level. Thought slows, arithmetic errors multiply, and crews acclimatize for hours at a mid-level station before ascending. Much of the night's work is now done from control rooms near the coast, or from another island entirely, with the mountain left to the instruments, the wind, and a summit that holds deep significance in Hawaiian tradition and whose use has been argued over for many years. Between the Tigris and the Euphrates, the land offers almost no stone and very little timber, but it offers mud without limit, and the people who settled the southern floodplain built their houses out of it, made their pots and their sickles out of it, and eventually wrote on it. A scribe took a lump of river clay, worked it smooth, shaped it to fit the palm, and pressed the cut end of a reed into the damp surface, leaving the wedge-shaped marks that we call cuneiform. Damp clay can be smoothed over and reused. Dried clay holds its impressions indefinitely. Baked clay, whether baked deliberately in a kiln or accidentally in the burning of a city, becomes something close to a brick and survives being buried for thousands of years. Papyrus rots, parchment is eaten, paper burns, and clay, which nobody chose for its permanence, outlasted all of them. What the scribes wrote about the sky began as a branch of a much larger practice of reading signs. Everything unusual was thought to carry information about the king and the state, and the sky, being visible to everyone and beyond anyone's interference, was the most trusted source of signs available. The great compilation of celestial omens, known from its opening words as Enuma Anu Enlil, ran to roughly 70 tablets and gathered many hundreds of statements of the form, if the moon is obscured in a certain month on a certain day, then a specified consequence follows for the land or its ruler. An eclipse falling on an unlucky date could set in motion a ritual in which a substitute took the throne for the duration of the danger, and the real king withdrew until the omen had spent itself. Prediction, in that setting, was not idle curiosity. Knowing when the sky might do something ominous gave the court time to prepare. Among those omen tablets sits one that behaves differently from the rest. It lists the dates on which Venus first appeared in the morning sky, vanished, reappeared in the evening, and vanished again, across a run of about 21 years during the reign of a king of Babylon in the second millennium before the Common Era. The copies that survive were made much later, some of them for the palace library at Nineveh in the 7th century, and they contain the errors and gaps that copying always introduces, but underneath the omens lies a genuine record of one planet's comings and goings kept over 2 decades. Scholars have spent a long time trying to use those dates to pin down the absolute chronology of early Mesopotamia, and the question is still open, which is its own kind of lesson about how much weight a single sequence of observations can carry. A compendium known by its first line, Mo, Apin, the plough star, shows how much had been sorted out by the early first millennium. It lists the stars in 3 broad bands of sky, gives the dates on which each rises before dawn through the year, sets out the rough scheme of the sun's path, and includes rules for the calendar and tables of shadow lengths and water clock intervals. The calendar was the practical problem behind much of this. Months began with the first sighting of the thin crescent after new moon, and so lasted 29 or 30 days. 12 of them fell short of the agricultural year, and an extra month had to be inserted from time to time to stop the harvest festivals from drifting into winter. Deciding when to insert it was originally a judgment call, announced by royal order. By the 5th century, a fixed pattern of 7 extra months distributed through 19 years had been adopted, and the calendar could be worked out years in advance. From the 7th century before the Common Era onward, the scribes of Babylon kept something new, a nightly journal of the sky, maintained without serious interruption for something close to 700 years. Each entry, written up month by month, gave the position of the moon relative to a set of reference stars near its path, the movements and disappearances and reappearances of the 5 visible planets, any eclipse, the weather, when clouds prevented observation, and then, in the same tablet and the same hand, the height of the Euphrates, the prices that a shekel of silver would fetch in barley, dates, mustard, sesame, and wool, and whatever had happened in the city that month. Astronomy, economics, and politics were filed together because the whole point was to see whether one predicted the others. Measurements were made against fixed points rather than in the abstract. A little over 30 stars along the moon's track served as markers, and the observer recorded how far above, below, in front of, or behind one of them the moon or a planet stood, in cubits and fingers, units that here describe angles in the sky rather than lengths on the ground. Timings came from the interval between moonrise and sunrise, or moonset and sunset, measured with a water clock and expressed in degrees of rotation. None of the individual entries is impressive on its own. Their value came from never stopping, from the fact that a scribe in the 2nd century could reach for a tablet written 400 years earlier and find the same phenomenon described in the same terms. Eclipses were the phenomenon that repaid this patience first. Lunar eclipses were noted whenever the sky was clear, and eclipses that had been predicted but did not appear were noted too, and once several centuries of them had been laid end-to-end, a pattern surfaced. A lunar eclipse tends to be followed by a similar one after an interval of roughly 18 years and 11 days, which is the time taken by 223 lunar months, and also, very nearly, by a whole number of returns of the moon to the point where its path crosses the sun's. The scribes arranged their eclipse records into columns spaced by that interval, so that the tablets themselves became a device for prediction, and gaps in the pattern showed where an eclipse should be looked for. The name now attached to that period was fixed on it by European astronomers much later, on the strength of a misread word. The same technique was extended to the planets, each of which has its own returns. Saturn repeats its pattern of risings and settings closely after 59 years, Jupiter after 71, and more accurately after 83, Venus after 8, Mercury after 46, Mars after 79. Tablets known as goal year texts collected, for a coming year, the relevant observations from exactly one such period earlier for each body, gathering onto a single surface everything needed to say in advance where the planets would be and when they would appear. Prediction had become a matter of consulting the archive. Numbers made the next step possible. Mesopotamian arithmetic used base 60 with place value, which allowed fractions to be handled as easily as whole numbers, and by the last centuries before the Common Era, The scribes had also divided the sun's path into 12 equal signs of 30 degrees each, giving them a coordinate frame that was independent of the constellation's ragged shapes. With those tools, they stopped merely matching old records to new ones and began to compute. Columns of figures were generated by arithmetical rules, some in which a quantity increases by a fixed step and then decreases by another, some in which the sky is divided into zones and a different constant rate applies in each. And from these columns they produced ephemerides, giving the moment of each new moon, the length of each month, the visibility of the crescent, the circumstances of eclipses, and the dates of planetary appearances, years ahead of the events. Nothing in this system describes what the planets are or why they move. No spheres, no orbits, no physical cause, only periods, extracted from records, folded into rules that produce correct numbers. Greek astronomers later took the eclipse observations and the period relations and fitted them into geometrical models. And the oldest observations that survive in Greek astronomical writing came from Babylon. The last datable cuneiform tablets of any kind are astronomical almanacs from around the beginning of the Common Era, written when the language they used had otherwise passed out of daily life, by scribes attached to a temple, still keeping count. A well at Syene, in the far south of Egypt near the first cataract of the Nile, was said to do something once a year that other wells did not, for at noon on the day of the summer solstice, the sunlight went all the way down the shaft and lit the water at the bottom, with no part of the wall throwing a shadow across it, because the sun at that moment stood directly overhead. Anyone who watched a vertical post in that town on that day would have seen its shadow shrink to nothing underneath it. Further north, the same post on the same day at the same hour kept a short shadow and never lost it, and the difference between those two shadows is the beginning of measured astronomy in the Greek world. Eratosthenes, who ran the library at Alexandria in the 3rd century before the Common Era, took that difference and turned it into a number. In Alexandria at the solstice noon, the shadow of an upright gnomon made an angle with the vertical of about 1/50th of a full circle, a little over 7 degrees. If the sun is far enough away that its rays arrive at both towns effectively parallel, then the only thing that can produce two different shadow angles is the curve of the ground between them. And the 7 degrees is not a property of the sun at all, but of the earth, an arc of its surface expressed as an angle at its center. Alexandria and Syene were reckoned to be 5,000 stadia apart, along a line running very nearly north and south. So the whole circumference had to be 50 times that, 250,000 stadia. Every step in that argument carries an assumption, and each of them can be checked. Parallel rays require a distant sun, which was already the common view. A single meridian requires Syene to lie due south of Alexandria, which it does not quite, though closely enough. The 5,000 stadia came from the reports of surveyors and from the ordinary traffic of the Nile Valley, rounded to a convenient figure. And the accuracy of the final answer is genuinely uncertain to us, not because the reasoning is doubtful, but because the stadion was not a standard length across the Greek world, so depending on which value is chosen, the result sits anywhere between a few percent and something like 1/6 away from the Earth's true girth. Aristotle, writing about a century earlier, had recorded that the mathematicians of his day put the circumference at 400,000 stadia, a figure with no visible method behind it, and the well at Syene replaced guesswork with a procedure that anyone could repeat. Before any of that could mean anything, the roundness of the Earth had to be more than an aesthetic preference, and the evidence for it came chiefly from two directions. Travelers moving north or south reported that the stars changed their heights above the horizon, that constellations invisible from Greece rose clear of the southern skyline in Egypt, and that the celestial pole climbed as one went north, which happens on a curved surface and not on a flat one. The second line of evidence appeared during eclipses of the moon. When the moon passes into the Earth's shadow, the edge of that shadow creeps across the lunar disk as a curve, and it is curved in the same way whether the eclipse happens with the moon high or low, early or late in the night, near the horizon of one season or another. A flat disk can cast a round shadow in one orientation only. A sphere casts one always. During those same eclipses, a further quantity can be read off, which is how large the shadow is compared with the moon that crosses it. Timing the passage, comparing the interval when the moon is entirely hidden with the interval it spends entering and leaving, gives the width of the Earth's shadow at the moon's distance in units of the moon's own diameter, and Aristarchus of Samos took that width as about twice the moon across. Allowing for the tapering of the shadow, the geometry returns the moon's size as a fraction of the Earth's, somewhat more than a quarter of its diameter, which is close to the truth. And since the moon's apparent width in the sky is about half a degree, its size and its distance follow from one another at once. Aristarchus then attempted the harder object. His method used the moment when the moon is exactly half lit, because at that instant, the line from moon to sun and the line from moon to Earth stand at right angles, and the triangle is fixed by measuring the remaining angle, the one between sun and moon as seen from the ground. He took that angle to be 3 degrees short of a right angle, and concluded that the sun lies between 18 and 20 times further away than the moon. The true gap between the two directions is about 1/6 of a degree, and the sun is nearly 400 times more distant. Nothing was wrong with the reasoning. The fault lay in judging by eye the exact moment of half illumination on a body whose edge is blurred by mountains, and in measuring an angle close to 90 degrees where a small error in the measurement produces a large error in the answer. That underestimate still carried a consequence its author did not shrink from. If the sun is 20 times further away and appears the same size in the sky as the moon, it must be 20 times wider than the moon, which makes it several times wider than the Earth and hundreds of times greater in volume. Archimedes, in a treatise on large numbers, reports that Aristarchus had proposed a scheme in which the Earth travels around the Sun and the fixed stars stand at an immense remove. The proposal did not take hold, partly because the expected shifting of the stars over a year could not be detected, which is exactly what one would expect if the stars are far enough away, and partly because a moving Earth conflicted with the physics then available. Measuring the moon's distance directly was possible in a way the sun's was not, and the reason is a matter of scale. Observers at two widely separated places see the moon against slightly different backgrounds of stars, by roughly a degree, twice the width of the moon itself, and that displacement is large enough to notice without instruments. Hipparchus, working from Rhodes in the 2nd century before the Common Era, used a solar eclipse that had been total near the Hellespont, while at Alexandria part of the sun's disk remained uncovered, and from the difference in what the two places saw, he extracted the moon's parallax and so its distance, arriving at a figure of roughly 60 times the Earth's radius. The modern mean is a little over 60. The same technique applied to the Sun yields a displacement of a few seconds of arc, far below anything the naked eye can register. So the solar distance stayed out of reach, and the value that came down through the later Alexandrian tradition put the Sun about 20 times nearer than it is. On Rhodes a century after Hipparchus, Posidonius tried the size of the Earth again using a star instead of the Sunday. Canopus, he was told, barely grazed the southern horizon from Rhodes, while from Alexandria it stood about 7.5 degrees high, 1/48th of a circle, and taking the two cities as 5,000 stadia apart, he obtained 240,000 stadia for the circumference. A later revision of that baseline produced a considerably smaller Earth, and it was the smaller figure that passed into the geographical writing of the following centuries and traveled, uncorrected, for a very long time afterwards. The altitude of a star above the horizon had by then become the most useful single quantity in the sky. It fixes a latitude, it converts a journey into an angle, it lets two observers who will never meet compare their positions on a curved world, and it needs nothing but a sighting edge, a plumb line, and a graduated arc. From wells, shadows, eclipse timings, and horizon angles, a set of numbers had been assembled that were carried forward, copied, argued over, and eventually corrected. A well-measured Earth, a well-measured Moon, and a Sun placed firmly in the wrong position by a method that was entirely sound. In 1259, on a hill above the town of Maragheh in the northwest of Iran, workmen began setting out foundations for a building whose only purpose was measurement. The patron was Hulagu, grandson of Genghis Khan, whose armies had taken Baghdad the year before. And the man who had persuaded him to fund it was Nasir al-Din al-Tusi, a scholar and mathematician who had spent much of his life moving between courts and fortresses. The arrangement was practical on both sides. A ruler wanted tables he could trust for calendars, for the timing of religious observance, and for the astrological judgments his court expected, and an astronomer wanted something that had almost never existed before, which was money that would keep arriving for as long as the work took. What separated Maragheh from the observing that had come before it was not any single instrument but the shape of the enterprise. Revenues from religious endowments were assigned to it, so the salaries did not depend on one prince's mood. A library was assembled and stocked with manuscripts gathered from the conquered cities. Craftsmen were kept on site to build and repair brass and iron fittings. Astronomers came from Damascus, from Mosul, from Andalusia by way of North Africa, and at least one is reported to have traveled from China, bringing with him a different calendrical tradition. For roughly 12 years the staff observed, computed, and argued, and the place outlived its founder and its first director both. Muayyad al-Din al-Urdi, an engineer from Syria, designed and built most of the apparatus, and afterwards wrote a treatise describing each piece and how it was made, which is why the equipment is known in detail even though almost nothing of it survives. There was a mural quadrant fixed in the plane of the meridian, an armillary sphere with 5 rings, an azimuth instrument for horizontal angles, and smaller devices for the parallax of the moon. All of them worked on one understanding. The accuracy of an angle depends on how finely the scale can be divided, and how finely a scale can be divided depends on how much physical length one degree occupies. Enlarge the radius, and each degree spreads out along the limb, until a minute of arc becomes a mark a careful eye can actually distinguish. Against the accumulating measurements stood the inherited system, and the trouble with it was not that it failed to predict. Ptolemy's models worked tolerably well. Their difficulty was internal. To reproduce the way a planet speeds up and slows down along its path, Ptolemy had introduced a point offset from the center of the deferent circle, the equant, about which the motion was uniform even though it was not uniform about the circle's own center. A sphere of heavenly material was supposed to turn evenly about its axis, and here was a construction that required a sphere to turn evenly about a point that was not its axis at all. 2 centuries earlier, in Cairo, Ibn al-Haytham had written a book of doubts about Ptolemy that made the objection sharply, and it had never been answered. Tusi's response was geometrical. He showed that if a small circle rolls without slipping inside a larger circle of exactly twice its radius, any point on the small circle traces a straight line back and forth along a diameter of the big one. A steady rotation, compounded with another steady rotation, yields an oscillation. With that device, later called the Tusi couple, and with a related theorem of al-Urdi's for handling eccentric motions, the astronomers at Maragheh and the students they trained rebuilt the planetary models so that every component turned uniformly about its own center, while the predictions came out much as before. Qutb al-Din al-Shirazi carried the work further, and a century afterwards, in Damascus, the mosque timekeeper Ibn al-Shatir produced a full set of models with no equant anywhere in them. The same rolling circle construction turns up in Copernicus, drawn in the same way, and how it reached him is still discussed. Out of the Maragheh years came the Ilkhanid tables, a zij, which is to say, a working manual rather than a book of theory. A Zij gives the astronomer everything needed to compute: the mean motions of sun, moon, and planets, the corrections to apply, rules for eclipses, and for the visibility of the new crescent, conversions between the Persian, Arabic, Greek, and Chinese calendars, tables of sines and tangents, geographical coordinates for a long list of cities, and a catalogue of fixed stars. Copies were made and carried, and the tables were used from Anatolia to India for a very long time, sometimes long after better ones existed, because a set of tables that a generation of practitioners already knows how to use has an inertia of its own. 160 years afterwards, and some 1,500 kilometers to the east, a Timurid prince took up the same idea on a larger scale. Ulugh Beg, grandson of Timur and governor of Samarkand, built first a madrasa and then, from about 1420, an observatory on a rise called Kuhak outside the city. He was unusual among patrons in that he observed and computed himself, and he gathered around him men who could do both, among them Qadi Zada al-Rumi, who had come from Anatolia, and Jamshid al-Kashi, who was probably the finest calculator of the age, and who wrote home to his father letters describing the work and the personalities involved. Cut into the rock of the hill, along a line running exactly north and south, was a trench, and inside the trench rose the arc of the instrument the place is remembered for, a meridian sextant of about 40 meters radius, its curved rails faced with marble and graduated along their length. Only the underground section still exists. On a circle that size, 1 degree of arc occupies roughly 70 centimeters of stone, and 1 minute a little over a centimeter, which is enough space to subdivide by eye. The instrument could only look at the meridian, the line passing overhead from north to south, and it needed nothing else, because every object in the sky crosses that line once a day, and its altitude at the crossing is the number that matters. Sun and stars were timed and measured as they came across. From the noon altitudes through a year, the tilt of the Earth's axis was derived. From the intervals between one spring crossing and the next, the length of the year, which the Samarkand tables give within about half a minute of the value accepted now. Latitude fell out of the same observations, and the slow westward drift of the stars called precession was measured afresh against the figure inherited from Greek work. Alongside the masonry there was arithmetic, and it was not the lesser half. Al-Kashi wanted a table of signs good to more places than anyone had produced, which meant knowing the sign of 1 degree exactly, a quantity that cannot be got by the simple halving and adding of the older geometry. He set the problem as a cubic equation and solved it by repeated approximation, each round of computation adding another correct sexagesimal place. In a separate treatise, he worked out the ratio of a circle's circumference to its diameter to 16 decimal places, a value unmatched for something like 2 centuries. Ulugh Beg's catalogue lists 1,018 stars with their positions and magnitudes, and most of those positions were freshly determined rather than copied and adjusted, which made it the first substantial resurvey of the sky since Alexandria 13 centuries earlier. He was killed in 1449 on his son's order. The observatory was abandoned soon after and eventually pulled apart for its materials. Ali Kushji, who had worked there, carried the tables westward to Istanbul. Manuscripts spread through the Ottoman lands and into India, and in the 17th century the star catalogue was printed at Oxford, where European astronomers compared it with their own. The trench itself was lost until 1908, when an archaeologist digging on the hill found the marble rails still in place, 60 degrees of a circle set into rock, cut for a kind of seeing that had gone as far as the unaided eye could take it. In November of 1572, a point of light appeared in the constellation of Cassiopeia, where no star had been recorded, and for several weeks it shone as brightly as Venus. Bright enough to be picked out while the sun was still up, a Danish nobleman of 25, recently back from years of study in German universities, saw it from an estate in Scania, and did something that most of the men who wrote about it did not do. Instead of arguing about what such an apparition might portend, he took an instrument and measured its position repeatedly over months against the stars around it. The measurement mattered because of an old assumption. Everything that changed, according to the physics inherited from Aristotle, changed below the sphere of the moon. Comets, meteors, and other transient lights belong to the upper air. Anything genuinely close to the Earth would show diurnal parallax, shifting slightly against the background stars as the turning Earth carried an observer from one side of the planet to the other during a night. Tycho Brahe measured the angular distance from the new light to each of the familiar stars of Cassiopeia, and those distances did not budge, not by the smallest amount his instrument could register. Whatever had appeared lay out among the fixed stars, in the region that was supposed to be incapable of alteration. He published his findings in a slim book the following year, and what he had watched is now understood as a supernova, the explosion of a star some thousands of light years away. 4 years later, King Frederick II granted him the island of Hven, a flat table of farmland in the sound between Zealand and the Scanian coast, along with the revenues to hold it. On that ground, Tycho built Uraniborg, a walled compound with a house at its center, observing platforms on the roof, a chemical laboratory in the cellar, a library, a paper mill, and a printing press, so that he need not depend on distant publishers. He was also a hard landlord to the tenant farmers whose labor paid for it, which the island remembered longer than it remembered the astronomy. Rooftop platforms proved to have a defect that only careful work exposes. Wind pushed at the large instruments and at the men leaning over them, and a structure high off the ground transmits every gust as a tremor. So a second observatory went up a short distance from the first, and most of it went down rather than up. Stjerneborg, its instruments set in crypts below ground level, their sighting apertures reaching through openable roofs, the observers sheltered from the weather, and the instruments resting on solid foundations. The design admitted that the limit on accuracy was no longer the eye, but everything supporting it. Size was the other lever. An angle is read off a graduated arc, and the longer the arc, the further apart the marks for a given fraction of a degree. So Tycho's quadrants, sextants, and armillary spheres were built as large as brass. Iron and seasoned wood would allow without sagging under their own weight. The great mural quadrant was fixed to a north-south wall inside Uraniborg, its arc more than 2 meters in radius. Divisions finer than the engraver could cut were obtained with transversal dots, small oblique rows of points along the scale that let a reader interpolate between marks. Sights were slits and pinnules rather than single pinholes, so that a star could be centered rather than merely glimpsed. Method mattered as much as metal. Every instrument was tested against the others on the same stars, and the differences between them were recorded rather than smoothed away, so that each device carried a known correction. Observations were repeated on many nights by several assistants, among them his sister Sophie, who worked alongside him on the island, and the young Longomontanus, who stayed with him to the end. Tycho also recognized that the atmosphere bends light from objects low in the sky, lifting them apparently higher than they are, and he compiled tables of that refraction to subtract from his readings. The upshot was a catalogue of 777 stars, whose positions were good to roughly 1 minute of arc, some 4 to 10 times better than anything before, and a run of planetary positions kept up nightly for 2 decades, which no one had ever attempted. A second visitor to the upper sky tested all of this. Late in 1577, a bright comet appeared, and Tycho tracked it for weeks, again looking for the shift that would place it near the Earth. What he found was a parallax smaller than the Moon's, which put the comet at several times the Moon's distance and set it moving on a long path through the space where the planets travel. If the planets were carried on nested crystalline spheres, as the old cosmology held, the comet had passed straight through them. He concluded that the spheres were not there at all, that the planets moved through open space, and this was arguably more corrosive to the inherited picture than the new star had been. Tycho did not follow the argument to Copernicus. He looked for the annual parallax that an orbiting Earth should produce in the stars, failed to find it with instruments accurate to a minute of arc, and reasoned that the stars would then have to be implausibly remote or implausibly large to remain visible. His alternative had the 5 planets circling the Sun, while the Sun, with its whole retinue, circled a stationary Earth. Geometrically, it reproduced the appearances as well as the Copernican scheme did. Physically, it kept the ground still under his feet. Frederick's death in 1588 loosened the arrangement, and by the time the young Christian IV came fully into power, the estates and the goodwill were withdrawn. Tycho left Denmark in 1597 with his instruments, his printing types, and his records, and after 2 years of moving through northern Europe, he was taken on by the Emperor Rudolf II and installed in Bohemia, first at a castle at Banatki nad Jezeru and then in Prague itself. The observations, 38 volumes of them in the end, travelled with him in crates. Into those rooms in the year 1600 came Johannes Kepler, a schoolteacher and mathematician from Graz. Driven out by the religious politics of his region and looking for data he could not gather himself, the two men argued over how much of the archive Kepler would be allowed to see. Tycho set him to work on Mars, the planet whose orbit had defeated every model, and died in October of the following year, after which Kepler succeeded him as imperial mathematician and gained access to everything. Mars was the right assignment because its path departs furthest from a circle among the planets that are easy to observe, so the errors in a wrong model show up there most plainly. Kepler first needed the Earth's own orbit, and he got it by a device of some elegance, taking Tycho's sightings of Mars separated by exactly 1 Martian year, 687 days, so that Mars sat in the same place each time and the shifting baseline was the Earth's. Then he fitted circles to Mars. One combination reproduced the observed longitudes to within about 8 minutes of arc, which earlier astronomers would have called a triumph, and which Kepler would not accept, because he knew the man who had made the observations and knew they were better than that. 8 minutes of arc cost him something like 5 more years. He tried ovals, computed by hand through hundreds of pages, and arrived finally at an ellipse with the sun at one focus, together with the rule that the line from sun to planet sweeps out equal areas in equal times so that a planet moves faster when nearer. Both appeared in his Astronomia Nova of 1609. A decade later, he added the relation between orbital period and distance, the square of the one keeping pace with the cube of the other, valid for every planet at once. The Rudolphine tables followed in 1627, built on the island observations, and they predicted a transit of Mercury across the Sun in 1631 that an astronomer in Paris duly watched. Decades of patient sighting turned at last into arithmetic that held. Word of a new Dutch device reached northern Italy in the middle of 1609, carried by travelers and letters rather than by any published description. A spectacle maker in the Netherlands had applied for a patent the previous autumn on a tube with a lens at each end that made distant things appear close, and the idea spread faster than the object itself, so that men who had never handled one knew roughly what it did. Galileo Galilei, then in his mid-40s, and holding the chair of mathematics at the University of Padua, in the territory of the Venetian Republic, heard the reports and worked out the arrangement for himself, which was not difficult once the effect was known. A weakly curved lens bulging outward at the front, a strongly curved lens hollowed inward at the eye, and a spacing between them close to the difference of their focal lengths. Making one that was worth looking through proved harder. Ordinary Venetian glass carried bubbles and striations, so he sorted through blanks for the clearest, ground, and polished the surfaces himself with abrasives and pitch, and reduced the errors of the front lens by covering its edge with a ring of card, using only the well-behaved central part. His first attempt magnified about 3 times. Within weeks, he had one near 8, and by the following winter he had instruments reaching 20 and beyond. The design has a defect that no amount of care removes, which is the narrowness of what it shows. At high power, the field is a small disk, so that the moon could not be taken in at a single glance, and finding anything at all in the sky required patience and a steady mounting. In August of 1609, he took an 8-power instrument to Venice and led members of the Senate up the bell tower of San Marco, where they watched ships in the lagoon and out towards the Adriatic that would not be visible to the unaided eye for another 2 hours or more. The commercial and military value was obvious to everyone on the tower, and his position and salary at Padua were confirmed and raised. The scientific value came from a decision he made shortly afterwards, in the autumn of that year, when he pointed the tube away from the horizon. The moon was the first thing he studied properly, and it did not look like a polished sphere. Along the line dividing the lit half from the dark, the boundary ran ragged rather than smooth, broken by notches and bays. Inside the dark region, close to that boundary, isolated specks of light stood detached from the illuminated part, and over the following hours those specks broadened, joined the lit area, and were swallowed by it. Sunrise on a mountain range on Earth does exactly this, striking summits while the valleys are still in shadow. In England, Thomas Harriot had turned a spyglass on the moon a few months earlier and drawn what he saw, though he did not publish. Galileo drew it too, in wash and ink, and then did something further with the drawings. Geometry turned the observation into a number. A bright point standing at a measured fraction of the lunar diameter beyond the terminator, on a globe whose angular size was known, gives the height of the peak catching the light, and Galileo's calculation returned mountains around 4 miles high, greater than the figure then accepted for the tallest ranges on Earth. He also argued that the faint grey light filling the unlit part of a crescent moon was sunlight reflected from the Earth onto the lunar surface, which made the Earth a body that shines on its neighbours in the way the moon shines on us. On the 7th of January 1610, while looking at Jupiter, he noted 3 small stars in a straight line beside the planet, 2 on one side and 1 on the other. The following night, all 3 lay to the west. Over the next weeks, their arrangement kept changing. One of them disappeared behind the planet and returned, and on the 13th, a 4th joined them. By the end of the month, the pattern was clear. 4 bodies swinging back and forth along a line through Jupiter, each with its own period, none of them ever straying far. They were satellites. He wrote the results up quickly, and a short book came off a Venetian press that marched under the title Sidereus Nuncius, The Starry Message, with the lunar drawings and the nightly diagrams of Jupiter's attendants, set out almost as a logbook. 4 moons around Jupiter settled nothing about the Earth's motion, but they removed a specific objection to it. Critics of the Copernican arrangement had asked how a moving Earth could keep hold of its moon, and here was a planet unquestionably in motion, whatever the system, carrying 4 companions without shedding any of them. It also meant the heavens contained at least one center of circulation that was not the Earth. Naming those satellites the Medicean stars was a calculated courtesy, and it worked. Later in 1610, Galileo was appointed mathematician and philosopher to Cosimo II, Grand Duke of Tuscany, and left the teaching and the examinations of Padua for Florence and a salary with no lectures attached. In the spring of 1611, he traveled to Rome, where the Jesuit mathematicians of the Collegio Romano checked his claims with their own instruments and confirmed them, and where, at a banquet given by the Academy of the Lincei, a Greek scholar among the guests proposed a name for the device assembled from the Greek words for far and for seeing. Venus supplied the observation that bore most directly on the arrangement of the planets. Watching it through the last months of 1610, Galileo found it small and nearly round when it was faint and far from us, then progressively larger and more gibbous, and finally a broad, thin crescent when it was closest and brightest. He sent the result to Kepler first as a scrambled Latin sentence, a common way of claiming priority without disclosing the finding, and unscrambled it afterwards. A full cycle of phases, with a small full disk among them, cannot happen if Venus always stays between the Earth and the Sun on a smaller circle, as the standard Ptolemaic layout required, since it would then never show its fully lit face. Venus goes around the Sunday. That much was settled, and it fitted the Copernican scheme, though it fitted equally the compromise arrangement in which the planets circle the Sun, while the Sun circles a stationary Earth, and the argument moved on to other ground. Saturn, meanwhile, showed him something he could not interpret at all, a shape with bulges on either side that vanished entirely 2 years later. Spots on the Sun came next, observed by several people independently in 1611, and disputed afterwards in a long exchange between Galileo and a Jesuit astronomer writing under a pseudonym. A pupil of Galileo's supplied the safe method: project the solar image through the instrument onto a sheet of white paper and trace the markings there, rather than look through the tube. Day by day, the spots crossed the disk from one edge to the other in about a fortnight, and near the edges they appeared narrow and moved slowly, exactly as a mark on a rotating sphere must when seen at a shallow angle. They belonged to the Sun, or to something very close above it, and they carried the information that the Sun turns on its axis in roughly a month. They also grew, shrank, split, and faded, in a region of the sky where nothing was supposed to alter. Away from the bright objects, the same tube did something quieter to the fixed stars. Orion's belt and sword, which show a handful of stars to the eye, filled with dozens more. The hazy patch in Cancer separated into some 40 individual points. The Pleiades multiplied. The band of the Milky Way, held for centuries to be some kind of luminous vapor, dissolved wherever he looked into stars too faint and too crowded to be told apart without help. Planets grew into little disks under magnification, while the stars stubbornly stayed points of light, which he took as a sign they lay at some far greater remove. The sky had just acquired a great many more objects, and no method yet existed for saying how far away any of them were. Bath, in the west of England, was in the 1770s a town of assembly rooms, subscription concerts, and paying visitors, and it supported a working musician comfortably enough. William Herschel had arrived from Hanover as a young man, an oboist by training who taught, composed, conducted, and eventually took the post of organist at a fashionable chapel there. Music led him by a route that seems roundabout only in retrospect. The mathematics of harmony took him to books on mathematics generally. Those took him to optics, and optics took him to a rented reflecting telescope. which he found so much better than nothing that he resolved to own a larger one than anybody would sell him. So he made his own, and having made one, made another. Making a reflector in that period meant casting a disc of specular metal, an alloy of copper and tin that takes a high polish and tarnishes steadily afterwards, then grinding it to a curve against a tool charged with abrasive, then polishing it by hand for hours at a stretch, with a steady figure-of-8 motion that could not be interrupted without spoiling the surface. The basement of the house in New King Street became a workshop, with a mold of dung and clay for casting, one attempt at which cracked and spread molten metal across the flagstones. Meals were taken standing at the polishing bench, fed to him by his sister, and the mirrors accumulated. 7 feet of focal length, then 10, then 20, each better at gathering faint light than anything then in regular use by professional observatories. Caroline Herschel had come over from Hanover in 1772, brought to Bath by her brother to train as a singer, and for some years she performed as a soloist in his concerts. As the telescopes took over the household, she was drawn into their service, first copying catalogues and grinding, later sitting at a desk by an open window with a clock, a lamp and a ledger, while her brother, outside in the dark at the eyepiece, called down what he saw. She learned to convert his rough descriptions into positions, to reduce the readings, and eventually to sweep the sky herself with a small instrument built for her. Their method was patient rather than clever. The telescope was pointed at a fixed altitude and swung slowly back and forth across the meridian, while the turning Earth carried a strip of sky through the field, and when that strip had passed, the altitude was shifted and the sweep began again. Over years, this covered the whole visible heaven, and the point was not to look at known objects, but to see everything, including whatever had never been catalogued. Herschel described himself as reviewing the sky in the way a naturalist reviews a coastline, noting what was there and returning to look again more closely. On the 13th of March, 1781, in the course of one such review of stars in the region of Taurus, he came upon an object that did not behave like a star. Higher magnification made it broader rather than merely brighter, which is what a disk does and a point does not. And 4 days later it had shifted against its neighbors. He reported it as a comet, and comets were expected to be found by amateurs. Continental mathematicians took the accumulating positions and tried to fit a comet's elongated path to them, and the path would not fit. What fitted was a nearly circular orbit, about twice as far from the Sun as Saturn. The solar system had a 7th planet, the first found in recorded history, and it had been sitting in old star catalogues for decades under other designations, recorded as a star by observers who had no reason to watch it move. Herschel proposed naming it for King George III, which secured him a royal pension and freed him from music. And the name that eventually stuck came from a German astronomer who preferred to continue the sequence of classical deities. The family moved to be near Windsor, settling at last in Slough, and the garden there became one of the productive sites in the history of observation. Payment for telescopes made in the workshop supplied a further income. Instruments went out to buyers across Europe. The largest of them was a reflector of 40 feet focal length, with a mirror 4 feet across, finished at the end of the 1780s, mounted in a wooden scaffold that became a landmark. It was awkward, slow to move, and its heavy mirror tarnished and sagged. And although 2 further satellites of Saturn were found with it soon after it was completed, Herschel did most of his work with the 20-foot, which he could handle in a single night's sweeping. The lesson that an instrument's usefulness depends on how often it can actually be used was learned there and has been relearned regularly since. Caroline's own sweeps turned up 8 comets and a number of clusters and nebulae that had been missed, and the king granted her a salary of £50 a year as her brother's assistant, which made her, so far as anyone can trace, the first woman in Britain paid for scientific work. She compiled a catalogue, reconciling and correcting the great English star list of the previous century, finding errors and omissions in it by comparison with the sweeps, and long after her brother's death she organized the nebulae into the arrangement by zone that her nephew used for his own survey. She was given a gold medal by the Royal Astronomical Society in her late 70s and lived into her 98th year. Some of the work at Slough was aimed squarely at distance. Herschel reasoned that if 2 stars appeared close together by chance, one behind the other, the nearer would shift against the farther over the year as the Earth swung around its orbit, and that this shift would give the parallax that nobody had yet measured. He assembled hundreds of these close pairs, watched them for 2 decades, and found something other than what he sought. Many of the pairs were changing their relative positions in a way that traced curves, arcs of orbits, which meant the 2 stars were bound to each other, and circling a common center. Gravity, until then demonstrated only within the Sun's family, was shown to operate between distant suns. The catalogues of nebulae grew to some 2,500 entries. For years he held that these misty patches were all clusters of stars too remote to separate, and that a sufficiently large mirror would resolve every one of them, until he observed a small round nebula with a single star sitting precisely at its center, and concluded that some genuine luminous material existed, unresolvable because it was not made of stars at all. He also compared the small proper motions of stars and found them arranged as if the sun itself were drifting toward the constellation Hercules, dragging its planets with it. In 1800, working with sunlight rather than starlight, he passed a beam through a prism and laid thermometers in the colored band to find which part of it carried the heat, with further thermometers to the side as controls. The reading climbed from the violet end toward the red, and when he set a bulb just past the red edge, in the space where no color showed at all, it climbed higher still. Something was arriving there that the eye could not register, refracted less than red light and warming whatever it fell on, and the spectrum was thereby extended beyond its visible limits. The star counts came from the sweeps. Herschel selected several hundred sample fields spread over the sky, and simply counted the stars visible in each. Assuming that stars were scattered with rough uniformity through space, that they were all of much the same true brightness, and that his mirror reached to the outer edge of the system. Where the counts ran high, the system must extend far. Where they thinned quickly, it must be shallow. The figure he drew from this was a flattened slab, ragged at the rim, split along part of its length, with the sun somewhere near the middle. 2 of his 3 assumptions were wrong, and he came to suspect as much in later years, doubting aloud whether his instrument fathomed the depth at all. The shape survived the corrections better than the reasoning did. On Garden Street in Cambridge, Massachusetts, a short walk west of Harvard Yard, an observatory grew through the second half of the 19th century into something that had not existed before, which was less a place for looking at the sky than a place for keeping it. The instrument that made this possible was not a new lens or a wider mirror, but a coated sheet of glass, and the change it brought was one of permanence. An observer at the eyepiece holds an impression for as long as the memory lasts and then writes it down. A photographic plate holds the light itself, fixed in silver, available to be measured next week or in 40 years by someone who was not born when the shutter opened. Dry gelatin plates came into general astronomical use in the 1870s and 80s, and they had a property that the retina does not share. Light falling on the eye is spent as it arrives, so a faint star stays faint no matter how long the watching continues, while light falling on an emulsion accumulates, so that an hour of exposure records stars far below the threshold of direct vision. A plate could also be handed across a table. It could be compared with another plate of the same patch of sky taken in a different year, laid over it, measured with a ruled scale, argued about by 3 people at once. Henry Draper, a New York physician with a private observatory and a serious interest in spectra, had photographed the spectrum of the star Vega in 1872, capturing on a plate the dark absorption lines that, until then, had been sketched by hand at the eyepiece. He died in 1882, with the work barely begun. His widow, Anna Palmer Draper, endowed a memorial in his name at Harvard, and the money went to Edward Charles Pickering, the observatory's director, who used it to fund a program of photographing and classifying stellar spectra across the whole sky, north and south alike. The technique that made such a program feasible was the objective prism. Rather than feeding one star at a time through a slit into a spectrograph, a thin prism of large diameter was mounted over the front of the telescope, so that every star in the field arrived already spread into color. Each point of light became a short streak, a miniature spectrum with its absorption lines crossing it like rungs, and a single plate might carry several hundred of these side by side. One night's work yielded not one spectrum, but a harvest of them, and the harvests piled up. Storage became a serious matter of shelving and floor loading. Over the decades, the collection grew to something near 500,000 glass plates, housed in the observatory's building in metal cabinets and paper jackets, each labeled with the date, the field, and the exposure. Taken together, they form a record of the northern and southern skies, stretching from the 1880s into the middle of the 20th century, which means that the brightness of a given star on a given night in 1892 remains a measurable quantity today, recoverable from a drawer. Somebody had to read them. Pickering hired women to do the measuring and classifying, dozens of them over the years, working at long tables in the daytime with magnifying eyepieces and logbooks, paid by the hour at rates well below what men in comparable positions received and largely excluded from the telescopes themselves. Among the first was Williamina Fleming, a Scotswoman who had come to Massachusetts, been left by her husband, and taken work in Pickering's household before he moved her to the observatory. She stayed for 30 years, supervised the growing staff, and found on the plates a great many objects nobody had catalogued, including the dark shape in Orion, later called the Horsehead. Fleming's first classification scheme sorted spectra by the strength of the hydrogen absorption lines and labeled the classes with letters running from A onward through the alphabet. It worked as a filing system and it fitted the data she had, but the ordering carried no clear physical meaning, and some of the classes turned out to be duplicates or errors that had to be dropped. Her catalogue of more than 10,000 stellar spectra appeared in 1890, and it stood as the first attempt to describe the whole sky in this way. Antonia Maury, who was Henry Draper's niece, and a Vassar graduate, took a smaller sample of bright northern stars and treated it with much greater care. She rearranged the classes into a sequence she thought more natural, and she noticed something the letters alone could not express. Among stars of otherwise similar spectra, some showed lines that were sharp and narrow, while others showed the same lines broad and hazy. She marked this with a lowercase letter appended to the class, and the distinction, dismissed by some of her colleagues as needless complication, was later recognized as the difference between swollen luminous stars and compact ones, which made it a clue to the intrinsic brightness of a star, and therefore to its distance. Annie Jump Cannon, who joined the staff in the 1890s and had lost most of her hearing after an illness, resolved the tangle of letters into the arrangement still in use. She discarded the classes that did not survive scrutiny, reordered what remained into the run O, B, A, F, G, K, M, and divided each class into tenths so that the Sun sits at G2. The sequence proved to be an ordering by surface temperature, from the hottest blue-white stars at the O end to the coolest red ones at the M end, though the physical reason for it, the way heat determines which atoms in a stellar atmosphere are ionized and which are free to absorb, was not worked out until the 1920s. Cannon classified spectra by eye at a pace measured in stars per minute, and by the end of her career had personally sorted several 100,000 of them. The Henry Draper Catalogue, published in 9 volumes between 1918 and 1924, listed the spectra of some 225,000 stars, and its HD numbers are still stamped on objects in modern papers. Henrietta Swan Leavitt came to the same tables and was given the variable stars. Much of her material arrived from Harvard's Southern Station at Arequipa in Peru, which photographed the parts of the sky invisible from Massachusetts, and among those parts were the 2 hazy patches near the southern pole known as the Magellanic Clouds. Her method was comparison. Plates of the same field taken on different dates, one printed as a negative and laid against the positive of the other, so that a star which had changed in brightness betrayed itself as a mismatch in the otherwise cancelling pattern. Working this way, she identified 1,777 variable stars in the 2 clouds. For a subset of them, she was able to establish periods, and in 1908 she noted, in a sentence set down without ornament in the observatory's annals, that the brighter of these variables had the longer periods. 4 years later, a Harvard circular reported the result properly, using 25 variables in the smaller cloud, with cycles ranging from about a day up to a few months. Plotted with apparent magnitude against the logarithm of the period, the points fell along a straight line, one for the brightness at maximum and one for the brightness at minimum. The reasoning that gave this its force rests on the cloud being a single system. Its stars lie at very nearly the same distance from us, so the differences in how bright they appear are not distance effects but real differences in output, and the relation between rhythm and apparent brightness is therefore a relation between rhythm and true brightness. Stars of this kind, pulsating with periods of days to weeks, had been known since the 1780s from Delta Cephei in the northern sky, and they are luminous enough to be picked out at considerable range. Time the pulse of one, read its true output from Leavitt's line, compare that with how faint it looks, and the distance follows from the way light thins with the square of the range. What the line lacked was a 0 point, a single Cepheid whose distance was known by independent means, and that calibration was attempted within a few years from the measured motions of nearby examples. Above Pasadena, a ridge of the San Gabriel Mountains rises to something over 1,700 meters, and for much of the year, a layer of cool marine air sits below it, holding the coastal haze down and leaving the summit in still, dry air. George Ellery Hale, who had already built one observatory in Wisconsin and another in Chicago's suburbs, came west in 1904 to test that air with a solar telescope, and found the steadiness of the images better than anything he had worked with. The site had no road worth the name, only a trail used by hikers and burros, and everything that went up on the backs of animals or, later, on trucks grinding along a toll road cut into the slope. Getting the glass up there was the slower problem. A 60-inch mirror went into service in 1908, and behind it, Hale was already arranging a disc twice the area, cast at a French glassworks and shipped across the Atlantic with bubbles frozen into its interior that made the opticians doubt it would ever hold a figure. It held. Grinding and polishing took years. The mounting was assembled on the mountain, and in November of 1917, the 100-inch Hooker telescope collected its first starlight. For the next 3 decades, no instrument on Earth gathered more. What that mirror was mostly pointed at, in the years after the First World War, were the faint spiral patches catalogued across the sky by earlier observers and known then as spiral nebulae. Their nature was genuinely undecided. Some astronomers took them for clouds of gas and dust within our own star system, perhaps planetary systems caught in the act of forming. Others held that they were separate stellar assemblies comparable to the Milky Way and lying far outside it, an idea that had been floated in the 18th century and never settled. In April of 1920, the two positions were set out at the Smithsonian in Washington, with Harlow Shapley arguing for a single enormous stellar system some 300,000 light-years across, inside which the spirals were local features, and Heber Curtis arguing for a smaller Milky Way and a sky full of comparable systems at great remove. Curtis pointed out that the occasional new stars seen flaring in spirals were far fainter than new stars in our own neighborhood, which fitted with distance. Shapley leaned on plate measurements by a colleague at Mount Wilson, who reported seeing the spirals visibly rotate over a span of years, a motion impossible unless they were close. Those measurements later proved to be an artifact, but at the time they carried weight. Edwin Hubble, who had studied law before turning to astronomy and had come to Mount Wilson in 1919 after military service, began a systematic photographic campaign on the largest of the spirals, the one in Andromeda. Long exposures with the 100-inch resolved its outer regions into a fine speckle of individual points, and by comparing plates taken on different nights, he could look for points that changed. What he was hunting first were novae, since a nova of known character would give a rough distance. On a plate exposed over 2 nights in early October of 1923, he marked 3 suspected novae with the letter N. Checking the position against the observatory's stock of earlier plates of the same field, he found that one of the 3 had brightened and faded before, repeatedly, on a regular schedule. He crossed out the N and wrote VAR with an exclamation mark in the margin of the glass. The star was a Cepheid, of the kind whose rhythm Henrietta Leavitt had tied to true brightness in the Magellanic Clouds a decade earlier. Timing the cycle gave a period of about 31 days, which on Leavitt's relation implied a genuine output many thousands of times that of the Sun, and the star appeared so faint that the distance came out at roughly 900,000 light-years. Even on Shapley's generous estimate of the size of our own system, that put the Andromeda spiral well beyond its edge. Hubble kept working, adding more Cepheids in Andromeda, then in the smaller spiral in Triangulum, and in a fainter system in Sagittarius, so that the conclusion no longer rested on one star, on one plate. Word traveled by letter before it traveled in print. Shapley, receiving Hubble's figures, is said to have recognized at once what they did to his picture of the sky. The formal announcement came at a meeting in Washington at the very start of 1925. In a paper Hubble did not read himself, and the spirals stopped being nebulae in the old sense. They became galaxies, each one a stellar population of its own, and the Milky Way became a single member of a population of such objects, extending as far as the plates could reach. Meanwhile, in Flagstaff, Arizona, a quite separate line of work had been running for over a decade. Vesto Slipher, using a modest refractor and exposures that could run for whole nights across several nights in succession, had managed to record spectra of these dim, spread-out patches, which is far harder than recording the spectrum of a star, because the light is smeared over an area rather than concentrated at a point. In 1912, he found the dark absorption lines in the Andromeda spectrum sitting at shorter wavelengths than their laboratory positions, indicating approach at some 300 kilometers per second. As he added objects, a pattern emerged that he could not explain. Nearly all the others showed their lines displaced the other way, towards the red, done by amounts corresponding to 1,000 kilometers per second and more. Measuring such a displacement depends on knowing where the lines belong. The pair of strong calcium lines in the violet, for instance, has a fixed wavelength that can be checked in a laboratory on a bench, and the fractional amount by which they sit off that mark in a galaxy's spectrum gives the speed along the line of sight. Slipher had velocities but no reliable distances. Hubble, after 1925, had distances but only a handful of velocities of his own. Milton Humason took on the spectroscopy at Mount Wilson. He had driven mule teams up the mountain trail during construction, worked as a janitor at the observatory, then as a night assistant, and he turned out to have unusual patience and skill at the eyepiece, guiding an exposure on a faint smudge for hours at a stretch, night after night, until the plate held a usable spectrum. Hubble, meanwhile, stretched the distance scale outward by other means, using the brightest individual stars he could pick out in a galaxy, and beyond that, the total brightness of the galaxy itself, since Cepheids could only be resolved in the nearest cases. By 1929, Hubble had put the two quantities side by side for 24 galaxies with usable distances, and the plot showed velocity rising in proportion to distance, a straight line through a scatter of points, with a slope of roughly 500 kilometers per second for every million parsecs of remove. The paper was short and its language careful, describing a relation between distance and radial velocity rather than making claims about what the sky was doing. 2 years later, with Humason's spectra reaching much fainter and more distant systems, the same line held out to velocities of some 20,000 kilometers per second, and the proportionality no longer looked like an accident of a small sample. Theoretical work already existed to meet it. Solutions to the equations of general relativity found in Russia in the early 1920s, and, independently, a model published in Belgium in 1927, which had predicted precisely such a proportional relation. On that reading, the galaxies are not flying through space away from a center. The space between them is increasing, and light crossing it arrives stretched. A calibration error sat inside the numbers for another 20 years. The Cepheid 0 point had been set with too little care for the fact that these stars come in more than one kind. And when Walter Bar-Ed, observing from the same mountain under the wartime blackout of Los Angeles, sorted the stellar populations properly in the 1950s, the distances roughly doubled, and the slope of the line fell accordingly. The relation survived the correction. Only the scale of the sky it described had been understated. New Jersey has nothing to offer an observatory in the way of altitude or dryness, and the instrument that changed the shape of cosmology there was never built for astronomy at all. On a rise at Holmdel, Bell Telephone Laboratories had put up a horn reflector some 20 feet across at the mouth, a great flared throat of aluminium mounted on a frame that let it swing to any part of the sky, designed to catch the very weak signals bounced off the first communications satellites. Its virtue was that it looked at almost nothing but the direction it was pointed. Radiation leaking in from the warm ground around it, the usual curse of a radio dish, was suppressed by the shape of the horn itself, and every part of its response had been measured with the patience of an engineering laboratory that intended to bill for the results. Arno Penzias and Robert Wilson took the horn over for radio astronomy once the satellite work had moved on, intending to measure the weak emission from the outer parts of our own galaxy at a wavelength of 7.35 centimeters. Work of that kind is an exercise in bookkeeping. Every contribution to the noise in the receiver has to be accounted for, from the temperature of the atmosphere overhead to the resistance of the wires, so that whatever is left over can be attributed to the sky. When they finished the accounting, a residue remained, equivalent to a source at roughly 3.5 degrees above absolute zero, and it would not go away. Elimination took the better part of a year. Pointing the horn at different regions of the sky changed nothing. Aiming it toward New York City changed nothing. Months passed and the seasons turned without altering the level. A pair of pigeons had taken up residence in the throat of the horn, and the birds were removed and the interior cleaned of their droppings, and the residue stayed. Aluminium seams were taped over. The cold reference load, chilled with liquid helium, was checked and rechecked. Whatever they were receiving arrived equally from every direction, at all hours, in all weathers. 30 miles away at Princeton, a group under Robert Dick had been building a small radiometer to look for exactly this. Their reasoning ran from theory. If the expanding universe had once been hot and dense, the heat of that state should still be present as radiation, cooled by expansion into the microwave band, filling all of space. A similar prediction had been published in the late 1940s by Ralph Alpha and Robert Herman, who put the present temperature at around 5 degrees above absolute zero, and it had drifted out of general circulation without ever being tested. A telephone call connected the two groups, and in 1965, the Astrophysical Journal carried their papers together, one reporting an excess antenna temperature with almost no interpretation attached, the other explaining what such an excess would mean. Here is the picture that the HISS supports. For its first few 100,000 years, the cosmos was hot enough that atoms could not hold together, and free electrons scattered light so effectively that the whole of space behaved like the inside of a cloud. As expansion cooled the material through roughly 3,000 degrees, electrons and protons combined into neutral hydrogen, the fog cleared, and the light that had been bouncing endlessly was released to travel in straight lines. It has been traveling ever since, stretched along with the space it crosses, until wavelengths that began in the visible and infrared now lie in the microwave. Something like 400 of those photons occupy every cubic centimeter of the room in which you are lying, arriving from all sides, having last touched matter before there were stars. Confirmation of the shape of that radiation came from above the atmosphere. A satellite launched in 1989 carried a spectrometer that compared the sky against a calibrated internal source, and the match to a perfect thermal spectrum at 2.73 degrees above absolute zero proved to be closer than any laboratory blackbody then available. A second instrument on the same satellite found after careful subtraction that the temperature is not quite uniform. Patches differ from one another by about 1 part in 100,000. Those faint variations record the slight over- and underdensities of the early material, the irregularities from which every galaxy later grew, and reading them in detail became the central task of the field. Reading them requires large apertures, long stares at the same patch of sky, and above all, air with no water in it. Water vapor absorbs and re-emits at millimeter wavelengths, and worse, it moves, so that its emission flickers across a detector and swamps a signal measured in millionths of a degree. That single requirement drove the instruments to the high desert of northern Chile and to the flattest, driest, coldest place available anywhere on the planet. The Antarctic Plateau is an ice sheet some kilometers thick, spread over the interior of the continent, and the station at the geographic South Pole sits near 2,800 meters of elevation, with an effective pressure altitude higher still because cold air settles. Winter temperatures near the pole run below -60 degrees Celsius, and the stations on the highest domes of the plateau have recorded lower. Air that cold can hold almost no moisture at all. The column of precipitable water above the telescopes frequently amounts to less than 1/4 of a millimeter, which is a small fraction of what lies above the best mountain sites. For 6 months, the sun stays down. From the pole, the sky does not rise or set, so a chosen field circles overhead without ever approaching the horizon, and a telescope can integrate on it for years. An interferometer operating there in the early 2000s made the first detection of polarization in the microwave background, the slight alignment of the electric field imprinted when the last scattering took place. A 10-meter dish followed, surveying thousands of square degrees and picking out distant clusters of galaxies by the shadow they cast, the way hot gas within them nudges background photons to slightly higher energies as they pass through. Alongside it, a series of small, wide-field refracting telescopes has stared at one clean patch of southern sky, hunting a particular curled pattern in the polarization that would be the fingerprint of gravitational waves from the first instant of expansion. A claim detection announced in 2014 was reassessed once better maps of dust in our own galaxy became available, and the signal was found to be consistent with foreground dust grains aligned by magnetic fields. The limits have been tightened steadily since, and the search continues with more detectors on the same ice. Beneath the station, the ice itself has been turned into an instrument, though not for light from the sky. Hot water drills sank 86 shafts to depths between roughly 1.5 and 2.5 kilometers, and into each was lowered a string of basketball-sized glass spheres holding photomultiplier tubes, a little over 5,000 of them, spread through a cubic kilometer of ancient compressed ice that is free of bubbles and perfectly dark. What they wait for are neutrinos, particles with no charge and almost no mass that pass through planets as easily as through vacuum. Very occasionally, one strikes a nucleus in the ice and produces a charged particle traveling faster than light moves in that medium, which sheds a cone of dim blue Cherenkov radiation as it goes. The arrival times across the buried spheres give the track a direction, and the total light gives an energy. Most of what triggers the array is made in the atmosphere by cosmic rays, so the Earth is used as a screen. Events arriving upward, having crossed the whole planet, can only be neutrinos. Since 2013, the detector has been reporting a population of very high-energy neutrinos that cannot be explained that way, arriving from beyond the solar system, and one such event in 2017 coincided in time and direction with a distant galaxy whose jet was flaring in gamma rays. Buried in ice laid down long before anyone thought to keep records of the sky, the array logs its faint flashes through the winter dark, unattended for months at a time. We are going to stop here. The music will carry on for a while, and then it will fade on its own. There is nothing more to do tonight. Rest well, and see you very soon.